IITM Pune. First of all, I thank Dr. Anupam Hazra for accepting our invitation and for being a part of this ESSO talk. Before going to the talk, I request Dr. Rashmi to give a brief introduction of Dr. Anupam. Thank you.
Thank you, Dr. Srilash, and respected Director, NCESS, scientist, staff, and the distinguished speaker. Welcome to the ESSO Forum. It is my pleasure to welcome today's speaker, Dr. Anupam Hazra, Scientist F, to the NCESS Earth Science Forum presentation, who is extensively working on clouds, convection, cloud modeling, microphysics perspective on the Indian monsoon and also on the lightning hazard. A brief discussion, a brief words about Dr. Anupam Hazra. He's a renowned scientist at Indian Institute of Tropical Meteorology, Pune, and he's got his doctoral degree in atmospheric science and he did postdoc from National Taiwan University and working on cloud microphysics, mesoscale and global climate modeling, aerosol cloud interactions. He has done most of his research in exploring dynamics of cloud microphysics and lightning aspect of the atmosphere. He has published widely more than 70 peer-reviewed research papers and a well-known recognized expert on cloud microphysics. I welcome him wholeheartedly to the Earth Science Forum presentation of NCESS. Thank you. Thank you all. Please join.
Okay. Thank you, Rashmi. Firstly, I would like to thank Director NCESS and ESSO Earth Science Forum and Dr. Srilas and Dr. Rashmi for inviting me in this here for giving a talk. So the title of my talk is The Cloud Convection Microphysics, a Major Challenge in Climate Model in the Perspective of Indian Summer Monsoon and Lightning Hazard. So first I must acknowledge my all collaborators and also acknowledge our project scientists and students who put their efforts in my all works. So it is not a one-man work, this is a group work. So I must acknowledge all collaborators and students who contribute here. Okay. So first part, there is a part, two part. So first part is the Indian summer monsoon and second part lightning hazard. Okay, as you know that why we need the skillful ISMR prediction. So as you know that 1/5 of the world population living in South Asia thrives on regular arrival of the summer monsoon. And we know that agriculture, food production, economy critically depends on the monsoon rain. And therefore, the skillful seasonal forecast has potential for high impact on agriculture as well as the water resource management. And therefore, the reliable forecast of monsoon on the subseasonal to seasonal time scale is very, very important. But what is the problem? The problem of global model, like a dry bias in simulating the monsoon season, like JJ's precipitation over monsoon region is a generic problem, as reported by many authors like Rajivan and Nanjundia 29. They have shown that it limits the scale of the predictability of ISMR. But in that direction also there is a ray of hope. What is that? As you've seen in this figure, that the scale of present generation model as shown Rajivan et al. 2012 is higher than the earlier generation model as shown by Krishna Kumar 25, and which indicate that the improvement of the models lead to the improvement of the scale. So there is a scope or hope that if we improve the climate model, the scale can be improved. Then what is the way forward? So still date, this is a grand challenge. Even today, the all model scale is rather limited. So first challenge is the conceptual basis of prediction, the scale beyond the limit of potential predictability. And second is the targeted improvement of simulation and prediction of the Indian summer monsoon. So now in this respect, what is the role of cloud microphysics in ISM? So I will talk about only the cloud convection and microphysics part. As you know that long before 1980, Sika and Gadgil investigated the maximum cloud zone, which is called the MCZ, over the Indian subcontinent during monsoon, and evolution of cloud regime in the Misho, which is also reported by Wang et al. In 2015. And it is also well known that, which is shown by Razvan et al. 2013, and then Avik 2013, Kumar 2014, they have shown the cloud hydrometers, which is basically cloud mixing ratio, rain mixing ratio, snow, group L, etc., have a large impact on the vertical profile of latent heating due to their phase change. And the interaction among the thermodynamics and cloud microphysics and dynamics plays a crucial role on ISM precipitating clouds. And the formation of the stratiform rainfaction and convective rainfaction plays a crucial role in the organization of clouds and precipitation in monsoon interseasonal oscillation, which is called the Misho. Now, where is the problem? Where are we stuck in the model? So if we look into the cloud microphysics, upper panel, you can see here, the left are the climate model and right is the observation from the cloud sat. So you can see the cloud sat that the vertical profile of the ice mixing ratio, which is taken from the Walliger 2019, is the average over whole longitude and plotted with the latitudinal variation and pressure level variation, but no model in the world so can simulate the observed cloud mixing ratio. So that is the major drawbacks. Almost all models have the difficulty in reproducing the ice water content. But if we look into very recent paper by Field and Hemsfield, who's a very good observer, 2015 GRL, they have shown that nearly 45 to 70%, you can see here, nearly 45 to 50% of rain is coming from the snow melting. So snow melting, basically the cloud hydrometer, which is coming from the mixed phase processes over Indian domain. Now, if we look into the large scale precipitation and the melting of snow, there is a highly correlated. So the rainfall, which is coming from the large scale, which is called the stratiform rain, basically is coming from the melting of snow. So the production of cloud ice or formation of cloud ice or snow is very important in the model, how model able to simulate that hydrometers. So what is the hypothesis? So first we put the hypothesis that how we can improve that. So cloud ice or snow, this can form only if model able to capture the convection rightly. So we put a hypothesis like that, a model with high fidelity simulation of the synoptic, which is basically the loads, depression, etc., and Misho, like active breaks, will have a high scale of seasonal prediction. So automatically it will give to the participate in the seasonal prediction. Therefore, the target is the improving the biases in the simulating of the synoptic and Misho, which will give the double benefits. First, it would reduce the biases of the mean simulation of rainfall, and number two, it will improve the skill of the seasonal prediction. So the improved simulation of subseasonal like synoptic and Misho will improve the mean of ISM as well as the skill of seasonal prediction. So these are the hypotheses. So what is the strategy now? That we can select a prediction system involving the coupled global model and make the systematic improvement of the physical processes that the GCM. So that is one aspect. And next level, the improvements of CGCM will be targeted to improve the deficiency or biases in the model in simulating the ISM. Under Monsoon Mission, we have selected CFSB2 as the base model for development and use the prediction for the ISM. Okay, so first let me show that what is the problem in the model. So it is already reported in the Monsoon Mission that target activity, improve the Monsoon Mission prediction. And you can see that why we choose the NCESS model. So there are comparison of different models, and one can see that from this Taylor diagram, which is taken from Rao et al. 2020, that CFSB2 is better than other global model, but there is a major two biases which I addressed earlier also, that surface rainfall bias, which is a dry bias, and tropospheric temperature, which is the cold bias. You can see here, the left is the rainfall, and this one right is the of tropospheric temperature. But if we see the bifurcation of convective and stratiform rain, there also model has a huge overestimation over ocean, the convective rain. So too much convective rain model is doing and too little stratiform rain. So now question is it a problem of CFS-B2? No, this is not a problem of CFS-B2 only. So this is a generic problem of all climate model. So if we look into the CME5 model, left panel is the tropospheric temperature and right is the ratio of convective to total. So you can see that there is a huge cold bias. Most of the climate models tend to produce too much convective rain also and too little stratiform rain. So these are actually main barrier for the improvement. So now we are looking into the, okay, then what about the CFS-B2 and in terms of the clouds and the stratiform convective rain. So first, you can see the cloud properties of the NCESS CFS-B2. This is a high cloud fraction from the Calypso, and then lower you can see that CFS-B2 high cloud fraction. You can easily see that there is a highly underestimation of the high cloud fraction. So now high cloud fraction, how we can generate that is basically linked with the hydrometer again. So we can extract the two phases, ice and liquid phases, and one can see that high cloud fraction basically composed of the ice. So if we look into the mixing ratio from the MIRA, one can see that MIRA is huge, means the model is huge, underestimated the top level or upper level cloud condensate, which is composed of ice. So that is the major problem. So now our aim will be to correct the upper level cloud condensate. How to generate? So that will be the target. So before that, we have to understand the cloud processes in the model. So detail of the cloud processes, how cloud is or cloud mixing ratio is generated in the model. So that, and then how model generate or simulate the rainfall. That is also we have to understand first. So if you look at the lower part, the precipitation, basically the combination of the all microphysical phase, you can say the microphysical tendency equation, like rain autoconversion. This is the snow, ice to snow autoconversion, and then accretion, rain accretion and snow accretion. Now first we have to quantify that whether these microphysical processes related to rainfall or not. So in this work, we have shown that how this tendency equation, because these are the equation what model used in a regional model or a global model. So we have to target their biases to improve there. So before that, we are trying to see that, okay, so if the high cloud fraction is more during JJS, how it is linked with the deep convective clouds. So one can see the cloud optical thickness from MODIS and cloud ice optical thickness, and then deep convective cloud amount from ISCCP and CloudSat. You can see that all are generated over the Bay of Bengal and then central India. So which gives a hint that the synoptic events, particularly lows and depression, is linked with the seasonal, and which give the high cloud fraction. Okay, so that's why we have to look into the deep convective cloud amounts which is associated with the synoptic events. Okay.
Dr. Hazra?
Yes.
If you don't mind, I just want from any understanding.
Okay.
So you are talking about snow in the cloud, correct?
I am talking right now. Earlier I am talking about the snow in the cloud. Yes.
So can your model distinguish between snow and ice in the cloud?
WRM model can distinguish the ice and snow group L. There are 6 hydrometer: cloud water, cloud ice, snow, group L, and rainwater.
Okay. Okay.
Model can distinguish.
Yeah.
Okay. Okay. Thank you very much. So we are first targeting that whether the problem is coming from the snow accretion or autoconversion or rain accretion or freezing. So that the freezing can give the cloud ice, and then after formation of the cloud ice, it will convert it to the snow and then group L. So if we understood quantitatively that where is the bias, we can target on that tendency equation. So I will come to the equation later on. Okay. So first part question is the whether Indian summer monsoon is dominated by the ice cloud or warm cloud or both. So to understand this, we first do a sensitivity experiment with ice-free, means only warm cloud, and another ice plus warm cloud. So we can see that if we do not consider the ice component, so it will not able to predict or simulate the convection correctly. How we can see? You can see the Euler. So no ice Euler and ice Euler, you can see there is a huge difference. And that is manifested in the high cloud fraction also. And that is again impact on the Hadley circulation, means dynamics. How? Through latent heat release. If you see the top, that this is a Q1 apparent heat source, with ice, the heating is more as compared to the no ice. So the model required the complete warm and ice, both microphysics is required. Only warm microphysics is not able to simulate or give the right dynamics, and then microphysics. Okay, so now question is, okay, then what is the role of convection? So in model, we have the different convective parameterization, like SESS, simplified error cost word, and new SESS, revised or new simplified error cost word. Then in conjunction with this ice and noise, which will give the better and why it is better. So to understand that, we have done again that ice coupled with different convective parameterization. And one can see that's very interesting thing, that convective parameterization which give the source of QV, means moisture vapor, and then the microphysics will take over and to form the other hydrometers like cloud ice, snow, and Gropel. So ice is very important in the model, say whatever the WRF or CFSB2. Okay, so now I will come to that tendency equation, how it is working. So if we see that two part, okay, forget about this now ice. So if we consider the cloud and rain, so there is a cutoff of the mass. It is also reported from the observation, Kaipex observation also giving that there is a cutoff size. So in terms of the size or mass, there will be the cell collection, there will be the AU auto conversion, and then accretion can happen. So now question is that how we can get the better parameterization with the guidance of the observation. That is required because the model we are taking from the NCESS, but we need to modify based on our own observation over the looking into the convection over the Indian summer monsoon. And number two, if there is some absence of tendency equation in the model, we have to add. What sir was asking, that whether the snow is there in the model. If not, we have to add. So we are newly added some tendency equation in the model if required. So that is the thing. So like the snow, which was not earlier in the model, we have added. So I will come to that point. Okay, so first way, we have quantify the microphysical process rates, all these process rate, and make the quantification. If freezing is there, what is the freezing amount, evaporation, accretion, so all we quantify. And then make a hypothesis that how it can work. So it is the water vapor is the source. So basically it is coming from the ICBC or relative humidity. And then there will be the deposition and condensation. These are the microphysical process, evaporation, and which will give the vertical profile of heating through the microphysical phase change or thermodynamical phase change. So that heating will impact on the temperature, that temperature will impact on the dynamics, and then how much shallow convection or deep convection will happen. So that will. So like that way, if we change this microphysical tendency, it will impact the dynamics or impact the convective parameterization or convection through latent heat release. So this is the pathway. So now with that hypothesis, we make a strategy of the model development only targeting the microphysics. So first thing, the improvement of the large scale organized convection and total precipitation is possible by increase of stratiform rain production in the model. This is already reported by several authors like Deng, Azeman, and Song Yu. So we are also going to target on that. Stratiform rain formation is intimately associated with the formation of the cloud condenser, as I discussed earlier. And particularly it is linked with the cloud ice and mixed phase hydrometers like snow, Gropel, etc. Okay, so which is already reported by Field and Hemsfield. So now we have taken some guidance, how we can improve this convection as well as the microphysics. We take the guidance from the KIPEX observation. The guided from the KIPEX observation, we are getting that number concentration of the cloud drops, raindrops, and their size. So we are targeting convective autoconversion and microphysical autoconversion first, and then others. How we are doing, and that I will come to that. So we have done some sensitivity experiment based on the changing the autoconversion rate, which is basically a very famous name in microphysics community, which is called the C0 experiment, very famous and popular experiment, which is called the C0 experiment, role of microphysics and convective autoconversion for the betterment of MISO and MGO. So you can see that this is the rainfall. So 6 series of experiment we have done, E1 to E6. So one can see that how there is a changing behavior of the rainfall pattern. So upper 2 is the observation, GPCP and TM. So now you may ask that how we get this coefficient. Okay, so again, I am coming to the sensitivity experiment. These are the observation we are getting from the KIPEX, and you can see the different type of clouds are there. So if the clouds are there, so critical mixing ratio of the cloud, means cloud liquid water mixing ratio, will be different, because this is a function of the size of the cloud drops as well as the number of the drops. So now you can calculate easily that what is the critical over different cloud over Indian subcontinent, and then you can get the lower and limit and upper limit of the CMA, means convective autoconversion. Similarly, the microphysical autoconversion. Similarly, convective autoconversion also you can get. So it is also comparable with the Rotsyan and Lord, which already have done in other regions. So now you can do your experiment, making the different combination. So from the lower boundary to upper boundary. So with that concept we have done, and then we'll make a best combination which will give the better. So now we'll come to that results. Okay, first, if we do that experiment, now we can see. So E1 to E6, there is an experiment. So in the experiment name, you can see that CA002 means coefficient, and next MA coefficient means microphysical autoconversion coefficient. So interesting thing is, only I am trying to highlight that this coefficient is so important that upper level is the cloud, high cloud fraction. You can see E1 to E6 how the high cloud fraction is changing. And at the which is not coming abruptly, it is coming linked with the convection, which is diagnosed by the outgoing long wave radiation, which is called the Whaler. So you can see here E1 and in E6. E1 is minimum Whaler over the Indian region, or you can see the global tropics, and here E6. So here basically convection, E6 convection is overestimated, E1 underestimated. So we have to choose. So the combination of these two coefficient is very important, or you can say the parameterization of microphysics and convection is very important, or the triggering coefficient is very important for getting the right kind of convection, and then stratiform and convective rain fraction also. You can see here the ratio of convective to total rain, the top panel, and E1 to E6. You can see the E6 are rather underestimated. So we have to have choose a right kind of combination to get the as much as possible reduced convective rain and improve the stratiform rate. Okay, so with this thing, we have made a new the scheme. So the new scheme is not a completely new. This we have worked on the base scheme, and the black is the original, red is the modified, and this blue is the newly added scheme, like a snow accretion. So although the snow was there, but some process was the missing. So we have added that. So like that way, these are the scheme we have now used, and which is now transferred to the operational agency for their forecast. So this paper is also published in the Progress Towards Achieving the Challenge of Indian Summer Monsoon Climate Simulation, the coupled climate model, which is published in GEMS. So now I will show the results of that. That if we really done this improvement, how it improvement in the MISO, how it improvement in the synoptic scale. So now one can see, remember that this model I am talking about, the T126, basically that is 110 by 110 kilometer resolution, coarse resolution. So I will come some 38 kilometer also. So one result I will show. Anyway, so this is the improvement of space-time spectra of the low frequency 30 to 60 day mode, which is basically the MISO. The upper two are the observation from the GPCP and TRIM, and lower three are the control and two type of modification. So we called it modified convective microphysics. That's why we named MCM, V1 and V2. One can see that V2 is very close to the observation in terms of their intensity and the time scale. So now if we improve the resolution, same model, if we improve the resolution, it can better than the T126. That is obvious, because more higher resolution will give the better convection. So this is one important thing. Next, the improvement of the speed of the northward propagation. So earlier speed, this is the GPCP, this is the control. So now you can see that GPCP and MCM-V2, how the speed of the northward propagation of ISO is also improved as compared to the control. Okay, so now you may ask that, okay, then how it impact? What is the physics behind it? So if we look into the physically based, if we improve this modification, like I am taking only E1 and E4. E4 basically best thing, which is basically MCM-V2. So one can see the heating. This is the heating profile. So this heating profile, you can see that it improved from the E1, or we can say it changed strongly at middle level and the lower level, upper level, which impact on the wind. This is a lower level wind 850 and this is upper level wind 250. You can see there is a stronger wind, and which basically lead to the zonal shear also. You can see the difference. And then it impacts on the tropospheric temperature. As I mentioned, the tropospheric temperature, there is a cold bias that is also improved. So ultimately it impact on the skill of the prediction also. So what is the skill of the control? That is the 0.56. Now if we improve, it jumps to 0.71. So nearly 70% we have improved the skill, and basically we have this work also published in the paper JGR, which is called, title is Unraveling the Mystery of Indian Summer Monsoon Prediction, Improved Estimate of Limit of Predictability, that I mentioned in the second slide. That the understanding of the estimation is also important. Now question is how it improves. If we improve, so there are four kind of experiment we have done. So snow is development is taken care by Saha et al. So I am not discussing on that. And SNMP basically mixture of snow and the microphysics. So I am just considering control and microphysics part. One can see that this is the correlation and this is the control first and then snow, then microphysics. So microphysics actually cross the limit of predictability. And if we see the spatial correlation, this is the control, this is the microphysics. More red dot means more skillful. And if we take the maximum of the maximum skill, then it is much better. So our target, this model, present model, can go up to 0.82, which is very encouraging. So reliable seasonal forecast on regional scale with further improvements of the model physics and data assimilation is going to be for a further challenge. Now question is how it improves. Basically, we identified in this work that this seasonal forecast is not only depends on the, it is also linked with the synoptic and meso. So earlier it was understood that synoptic events basically that is giving a noise, but we can see that it is not the noise, the part of the predictable component as it is linked with the ENSO. So it can be predictable. So if we look in our, because as we know that synoptic event basically loads and associated with the loads and depression, which is I am taken from the IMD, you can see. So these are the main rain bearing system which brings the rain over the central India. Now if we look into the same thing over observation, so ice is the shaded and contour is the rain. You can see lag 0 to -2 to +2, which is basically synoptic event, 5 days event. So and one is the Bay of Bengal box, which is the basically the head Bay of Bengal, the genesis of the systems. And if we consider the central India, that is also how it is moving. Now, if we modify the microphysics, how it is. So the E model able to capture the lead lag composite of 3 to 7 days filter cloud ice or rainfall, it will give the better correlation. So that is our hypothesis here, that better representation of the synoptic in the model able to simulate or improve the skill of the seasonal ISMR also. So now, is it enough? No, this is not enough. We need further understanding of the aerosol on ISMR. As we know, the time scale is very important, and the emission of the aerosol again impact on the cloud as a cloud condensation nuclei and ice nuclei. So the betterment of the condensation or ice nucleation, which basically lead to the freezing, is also important. So with that, we have done another study that how aerosol is important. So there is a very very nice work by Manoj et al. So they have first shown that absorbing aerosol facilitate the transition of Indian monsoon break to active. So in the meso active break spell, how it will transit. So aerosol is important. So now in their paper, they are showing the radiative effect of the aerosol. So in the next attempt, 2013, we have published in JAS that we put the hypothesis and tested in the model again in WRF, and all kind of tendency term we are looking into that ice deposition, snow rhyming, group L rhyming, deposition, ice formation, cold rain, warm rain formation. And we can see that the BFA means break followed by active, which is just break followed by active, and BNFA, which is break not followed by active. So these are two differently behave. So the break followed by active, which is more moisture, actually aerosol try to invigorate the convection. On the other hand, and makes more organized convection and heavy rainfall. But break not followed by active, which aerosol basically suppress the convection. So aerosol has a two role. In one hand, it invigorate cloud. In the other hand, it can suppress. So more lighter rain and remains neutral. So no transition to active. Or for BFA case, the more moisture invigorate, transition from break to active. So to better predict the meso means active and break, we need the interaction of cloud dynamics and microphysics. So in the model, we have to include this process. So this is a need. So in the first part of the conclusion, so there is an interplay of the coupled dynamics, radiation and microphysics is important. The feedback mechanism from the microphysics to dynamics through latent heat release is most important. The major phenomena which affect the convection. Then cloud microphysics is in the subseasonal scale, synoptic meso is therefore very important for the skill of the ISMR. Then aerosol also important for the transition of meso. And we have to revisit all tendency equation along with the ice nucleation parameterization for improvement of the ISM in future. Okay. Okay, in the next part, I will very short lightning hazard. So I will just touch upon few slides. How many times I have?
You can continue, sir. 15-20 minutes you can continue, sir.
Okay, that's okay, fine. Okay, so as you know that this is the seasonal climatic of lightning. So this is actually MES gave us a new task of to develop a system for lightning prediction. So in 2018 we got a new task that this is also mission mode project, and we have to develop one prediction system, dynamical prediction system for lightning flash prediction. So I will just give the first the seasonal climatology of the lightning flash, as you know, over the global tropics. Why I will come to the global, so I will conclude the last. So firstly, we are targeting on the Indian. So one is the pre-monsoon MAM, another is the JJS, and this is from IMD. You can see the all over the India there is a lightning and thunderstorm, and all we know that the lightning, why it is hazard. So if we look into the history from 2022 to 2019, although the total death decreases in recent years, but death due to lightning increases. So why death decreases? Because the advancement of the prediction of cyclone, and which is actually more hazard, and but we are not able to improve the lightning hazard. So this was the thing, and therefore we are targeting on the prediction of the lightning. Now, what is the physics? Thunderstorm or lightning both have the microphysics origin, and they are also needs instability, trigger, wind shear, and moisture. So now we are looking into the conventional approach. The conventional approach was based on the CAPE, CINE, KI index, lifted index, humidity index, Ball-Richardson number, etc. But when dynamical model comes into the picture, so state of art numerical model came, then people try to use the dynamical model, and which is already reported by several authors like Rezvan et al. 2010, then Litya Mohan Kumar 27, Haldar 2015, many papers. So on the WRM model has a potential to see the severe thunderstorm events. So these are the base that we can use the dynamical model. So with that framework, we have proposed that we can use a dynamical model, but there are also questions that whether it can be, if we make a system, whether it will be same for all over India or region based we have to make. So before that, we are targeting on that the system should be same for all the regions, Southern Peninsula, East India, West India, or Central India. So our aim is the first we select the microphysical parameterization development, then we incorporate the lightning parameterization, which is based on the Price and Rain 1992, and there are many lightning parameters available offline and online. So we choose the reflectivity based lightning parameterization and incorporate in the model. So these are the new development we have done in WRF. And then we have compared with our lightning sensor network. Dr. Power and their group has established the LDN lightning detection network over Pan India. We compared with that. If there is bias, again we verify the skill score and go back for the modification. So these are the way. And in the next level, we are putting the statistical approach like a neural network or AI based, so which is called the hybrid approach. So dynamical as well as the statistical approach, which can give the better prediction. So firstly, we will talk about this part. Okay, so before that, we first see that, okay, if we see the NCESS FNL, so how it good in GFS and GFS 1534. We compare first in different system. One is the 4-domain system, another is 2-domain system. Now you may ask why we are going for the 2-domain system or single domain system, because for the real-time operational forecast, lightning or thunderstorm over Pan India, it requires, as per IMD, 1950 1 to 1851 grid points, which is a huge grid points. So if we simulate 1 kilometer in 4 domain system, nested system, it will take huge time. So model simulation time is highly important to get the product in hand with sufficient lead time. So we have to reduce the means number of nesting with keeping the similar result or equal results to improve the physics. So that was the target. So we have made that. And now you can see that 4 domain 1 kilometer and 2 domain 1 kilometer almost same in terms of the reflectivity. This reflectivity is a major indicator for the convection. And then we compare Maharashtra, Southern Peninsula, Eastern India, where we get the lightning flash, and we compare the with FNL, GFS, and GFS 1534, how model able to simulate the lightning. We have compared that, and then we applied for the real-time forecast. So now you can see that this is a Maharashtra case we have chosen because we have the observation, more observation over Maharashtra that time. So then you can see that different lightning parameterization, DLP1, dynamical lightning parameterization, 1, 2, 3, and this is the observation. And this is the LPI, lightning potential index, is the another method. So we can say that DLP2 is better than DLP1 and 3 as compared to the observation, as well as the independent method, which is called lightning potential index. And why it is better? Because it able to simulate the reflectivity correctly. This is the maximum reflectivity. So better spatial pattern and frequency distribution of lightning flashes is found in the reflectivity based lightning parameterization, and number of matching grid points due to randomness is also higher, nearly 70.9%. So and therefore we have choose the reflectivity based lightning parameterization in the operation forecast. Now you may ask, what is the usefulness? What is the skill of that? So we have also evaluate the skill and usefulness, which is published in weather forecasting in this year, May 2022. And very good thing is that reflectivity is moving with time. So means the initiation, mature, and development dissipation. So these are coming very correctly, nicely in the model. And we can see the POD versus POFD curve, which basically give a hint that how better your skill, whether it is useful or not. And we have used different microphysics scheme also. And one can see that microphysics is not that much important. The particular choose of lightning parameterization is important. And yes, here one worst means you can say some success, some failure is also there. False alarm is high. So if we see the real-time forecast, you can see here. So this is a real-time forecast which is giving in the website in IMD and IITM website. It is available. So we compare the lightning real-time forecast with real-time observation. You can see model is pretty good to capture the to simulate or to capture the lightning flashes. So we give in 3 colors to understand very easily for the common people: isolated, moderate, and severe. And this is one case of lightning associated with the cyclone that also model able to capture very nicely. Right panel is the observation, and here is the lightning, and this is the from the network. Okay, so these are the operational forecast last 2019 and 2022. You can see in the table, you can see that the POD, although POD is very high, 0.92, but there is a issue in the false alarm, 0.65 false alarm. But misses are very interesting. The misses are very less, which is very good. So if we take the report from our means death things, what I mentioned earlier, that it is reduced in the 2022 as compared to the other years. So that is actually, we can say, the improvement of the lightning forecast. Now, next level is the seasonal forecast of lightning. So question is it feasible, seasonal forecast of lightning? Is there any seasonal predictability of lightning over the global hotspot region, not only the India? So if there is a hypothesis of any seasonal forecast that it should be linked with the ENSO. Whether is that, so we trying to see that whether the seasonal forecast is possible or not. So we can find that this is a correlation of mean lightning fast and cloud top temperature, which is the basis of the convection, with the global SST. So one can see this very high correlation with the ENSO. If we look into this, this is the box we have considered over East India, and there is a high correlation. If we look into the compare with the rainfall also, it is better than rainfall. So we can tell that yes, in future the seasonal prediction of lightning is possible. Now question, we have to develop the lightning parameterization for the global model. That also we have done. So this is the observation, LIS, the seasonal mean, pre-monsoon and monsoon. And this is from GUS5 model. Basically, you can say the MIRA2, and this is the CMIP6. So although there is a bias, but the new parameterization, new developed parameterization able to get the mean pattern of the pre-monsoon and monsoon lightning correctly. Okay, so these are a hope that in future we can apply. So this will give an idea that in one season advance, which area will be more lightning prone. So, and then we can run the WRF over there and to get the better prediction. Okay. So now question is that whatever overestimation I am talking, like false alarm. So this is the old scheme. Now, if we modify, you can see if we develop the ICCG ratio based on the observation, you can see now this overestimation reduced very significantly. So these are, and next level we are improving through ice nucleation parameterization. So we have a spin instrument in HACPL. We have developed our own ice nucleation parameterization and tested in the idealized simulation and then apply in the WRF simulation, and we can get all mixing ratio, cloud ice, snow, groupal, and rain, and we can see that which one is giving the better lightning forecast. So that you can see here, this is just one give a hints that this basically this M92 is the common used ice nucleation parameterization in the model, but this is not enough. So this is not enough because if you compare the lightning potential index or lightning flash count, you can see the convection is not captured at all. So we have now, there is a need to modify or to choose proper ice nucleation parameterization in the regional as well as the global model. And secondly, that why it is important, we are not incorporating the aerosol or species into the model. So we have developed the new classical nucleation theory based ice nucleation parameterization, which is able to incorporate the species information as well as the ambient parameter like weighting factor, activation energy, particle radius, etc. So with this, actually, I will just coming to the conclusion. So first, to test the fidelity of the model, we compare the model ice aspect ratio with the observation. So observation says that over Indian subcontinent during monsoon, there is rimed needles, plates, columns, ice crystals are available. So which model able to simulate with this new parameterization scheme, and which have a double benefit, improve the depositional growth, improve the terminal velocity, collision coalescence efficiency, as well as the radiation. So we have just give a simple simulation with CCN and IN concentration, one low and high. You can see how convection is modulating due to the different concentration of IN and CCN. So for the convective event, the concentration or number concentration of aerosols which act as a CCN or IN is very important to simulate the convection correctly. With this, the conclusion of my last part 2, the understanding physical process of lightning and thunderstorm or improvement of the model is very important. The quantitatively assessment of the model performance in simulating lightning fast using DLP, dynamical lightning parameterization, has shown that almost all model, all scheme are very good, and DLP2 is the best for lightning parameterization. Spatial agreement is also very good, which is 0.5, and minimum is 0.74. And POD, FAR, and POFD and AUC are also calculated. The results reveal that accuracy in 50 kilometer square box are more than the 10 kilometer square box. And lastly, that improvement of ICCG ratio, ice nucleation parameterization, cloud aerosol interaction, and multi-moment cloud microphysical scheme is important for model development activity and need to be explored for the deep convective cloud system like thunderstorm, depression, as well as the MCS. So the possibility of reliable seasonal forecasting of lightning over global hotspot is also demonstrated, and lightning flashes are found to be tied with slowly varying remote global predictors, which is ENSO and AMO and NAO and PDO and extra topics, which is giving a hint that seasonal prediction of lightning is possible. Thank you so much for. So if you have any question, please ask me.
Yeah, the presentation is open for discussion. Anybody would like to have few questions? May proceed.
Hello.
Yes.
Yes, sir. Good morning. And this is Dharmadas. And in that AI scheme that you are talking about for lightning prediction, so what are the input and what are the output you have taken there? Means output maybe lightning flash rate, but input what you have taken?
WRF or which one?
No, that for lightning prediction, AI scheme you are talking about at some point. Artificial, that machine learning or something.
Okay, here.
The second one, yes, sir.
Here. Oh, okay.
So input output, can you just briefly tell?
Here actually there are people are working on that. They are first trying to find out which parameter is giving the best, which combination. Okay. So then only we can tell you that which are the best. But till now that I can tell you that ice mixing ratio.
Okay.
And the size of the hydrometer.
Okay.
And then the mass flux.
Okay.
And particle velocity. Okay.
Okay. So this is from model, right?
Yeah, we are first taking from the model, and then the AI tool or PCA LDA technique, they will first find out that which parameter is good.
Okay.
Okay. There are many parameters.
Yes.
Among all parameters, which combination is good. So accordingly, they will take that parameter and do that.
Okay, understand. So one more question is there.
Yeah, sure.
So that price range, that method you have used for that DLP, right?
Right.
And when you compare with that ERATL, that
LPI, yes.
So which one is better? Price range is better than that?
There is a issue. So you can see here, in some point, price and means DLP2 means price and read is better.
Okay.
But we cannot compare because this is a plus count, and that is the lightning potential index, that is the energy. Okay. So we therefore in terms of the magnitude we directly cannot compare. Because this is energy, LPI.
Okay.
And this is a plus count. So directly we can compare whether there is a overestimation or underestimation. Because we are getting observation the plus count, number of flashes per day or per hour.
Yes.
Okay. But if we see the spatially matching, so then we can see that how it is giving the better. But in terms of the overestimation, underestimation, we cannot do because the unit is different.
Okay. So variables are different, so we cannot exactly compare.
Yeah.
And sir, one more thing that here you are using basically a proxy method to get the lightning flash, right? Means you are not calculating that explicit electric field and all to get
No.
So whether that other one, that explicit method is also a viable possibility, or I'm just asking.
You are talking about the McCall method.
Means explicitly solving that potential in that means
Mackal. That is basically electric field. That is basically very famous name is the Mackal method.
Okay, sir.
Which Fierro et al. Fierro et al. So basically Mackal and Fierro. So you need to yes, I have compared. Means we have compared the Mackal and Fierro both, but there is some underestimation. But I cannot say with that underestimation that scheme is bad. No, there must be retuning is required.
Okay.
Like we have done some modification in Mackal.
Okay.
Giving a right kind of threshold of group L, which can show that it is comparable with the DLP2. But as per our present day, we are happy with the DLP2 if we compare the Fierro and Mackal. But definitely, I cannot comment that DLP2, Mackal or Fierro is bad. No.
Okay, so that explicit scheme, did you try on WRF or other?
WRF.
WRF. Oh.
WRF.
Okay, sir. Thank you.
Thank you very much.
Yeah, Ms. Anusha has raised some hand. Please ask.
Hello.
Yeah.
Sir, I am Mercy Varghese from IITM.
Okay, Mercy. Okay.
Sir, I have two doubts. One is regarding this lightning parameterization.
Okay.
So, we have a NSSL double moment scheme in WRF, right?
NSSL, yes.
So, how is this parameterization different from that NSSL double moment scheme?
NSSL with lightning you are talking, or only NSSL you are asking me that comparison of NSSL versus WDM6 or Mauritian or Thumb?
No. Because like what maybe my understanding is wrong. Sorry if I am asking a stupid doubt. My understanding is that NSSL is actually a scheme where it is concentrating on this electrification and lightning.
Not mandatory.
Not mandatory.
Yeah. So means Fierro et al. You have to just change a little bit. You have to modify a little bit. So you can coupled with other scheme also. Yes, they when they have developed the Fierro et al. Means electric field, which is basically box MG you are following. So that is basically coupled with the NSSL scheme. That's true. But you can apply with other microphysics also. But you need some modification. Hello.
Hello.
Yeah, I think disconnected.
Okay. I think Mercy is not able to connect properly.
Okay.
Sir, this price rent scheme, whether it is available directly on WRF or you have implemented it?
When I have implemented, I am thanks to Mary Barth. You know that Mary Barth, she implemented, developed that scheme. So we have worked on this. She is also the author. So that time I got from her, and we have implemented. Now I think it is available in 3.9.1 or 4.0. It is available.
Okay.
Hopefully it is available.
So it will flash rate directly.
Yeah, you can get the flash rate directly.
Okay.
Now in 3.1 and 4 version, both are there. This lightning parameterization and Fierro et al. Means electric field, both are there. So you can use that. But remember that when you are choosing that scheme, you have to very careful about the combination of microphysics and how you are giving it, means feeding that convection. That is important. Otherwise, you will not get.
So, whichever DLP that you used and which microphysics scheme actually was based for that?
Not that much difference. You can see here WSM6, Thomson, Morrison, WDM6.
Okay,
you see POD, in terms of POD, there is not much difference.
Okay.
But only thing that you will not get the convection rightly. You can see the DLP2 versus DLP3. See, there is a reflectivity. Maximum reflectivity is not coming in DLP3. So that is important. But you can improve the DLP3. There is a trick. So you can change the some code level modification, and then you can modify the DLP3 to improve the reflectivity also.
Sir, just
Yeah.
for clarification, DLP3 is which one actually?
Okay, this is basically the I think LNB based buoyancy level, neutral buoyancy level, LNB based.
Okay.
Therefore, you need the convection on, not off.
Okay. And all this simulation was 1 kilometer resolution? Or?
1 kilometer resolution. The we have presented the all 1 kilometer, but in real forecast, this is a real forecast. You can see in IMD website, all are 3 kilometer, not 1 kilometer, because we have make that combination modification to get the similar result of 1 kilometer. As I mentioned, that we need a lead time.
Okay.
So model, we need more means higher speed model, but we have to have compromise with that.
Okay. And how many domains you have used here?
Single domain.
Only single domain. Okay.
Single domain 3 kilometer.
Okay.
Otherwise, we cannot ready our product with proper lead time. So now we have a 6 hour at least lead time.
Okay. And what is your initialization time? 0 UTC? Previous
0. Now actually 2 cycle we have run, 0 and 12, but mostly working on 0 based on the availability of the IC which is supplied by the IMD. IMD GFS 1534.
Okay.
Sir, is this impossible to use with the spectral bin also?
Why not? Yes, but the question is that whether it will be useful for real-time prediction spectral bin.
No, sir. It's kind of like for a small system we have to understand.
Definitely.
All that
Definitely. For physics understanding, it is okay. But I am talking about in terms of the forecast. So in terms of the forecast, my question is whether spectral bin is useful. Because it is taking huge time.
Yes.
Competition time. But yes, physics understanding, always spectral bin you can use. Absolutely no problem. There is no guidelines that you can only switch to, only you can use this Morrison or WDM6 or Thomson. As I told Marcy also that it is possible. You can use any scheme, any microphysics scheme. Means you are talking about the Huji.
Yeah. Yes.
Yeah.
Hello. I think earlier Ms. Anusha has raised some hand. Is she there?
Okay.
Is she available? She can ask question now.
Okay, sure.
I think there is some problem with her mic. It seems.
Hello.
Hello. Yeah, I am audible. Yeah, means I can hear you. Okay.
Thank you, sir. Very good lecture on cloud microphysics and lightning.
Thank you very much.
My single doubt is, sir, how many hours before we can issue a warning or forecast, lightning forecast by using this model?
Means presently we are giving forecast like this way. Okay.
Okay, sir.
3 to 6, 6 to 9, and means 3 hours accumulated. Okay, we are generating the forecast like this way. 0 to 3 means 3 to 6, 6 to 9, 9 to 12, then 12 to 15, like that way. So your question is
actually, sir. Usually, to avoid the lightning hazards, we have to take care. We have to take care, or we have to evacuate some places. So, if we get
okay. I would like to. I guess my understanding is you are talking about the lead time. What is the lead time?
Yes,
okay.
Sir.
Yes, good. So we are generated. Means 6 to 9 hours you will get the lead time. 6 hours at least you will get the lead time.
Okay.
At present.
Okay, sir. Thank you, sir.
Yeah.
Yes.
One more doubt I have is by changing the auto-conversion parameterization or constants, is it affecting that cold phase of the clouds? And if so, how is it?
Means in for lightning or for monsoon?
No, the first half where you were trying.
Okay, very good, very good. At least first half there is one question. Okay, very good. I was worried that there is no question from the first half. Thank you. At least, yeah. Okay. So means your question is when I am changing this one in monsoon part. You are talking about monsoon part.
Yes.
Yeah. Could you please repeat once again your question?
Yeah, so like you are changing the auto-conversion constant parameterization.
Right.
So like what is that effect on that cold phase microphysics when you do that?
Oh, very good question. So you can see easily in the high cloud fraction. So although I have not plotted the cloud ice, but yes, definitely it impact on the formation of the cloud ice, and that's why you are getting the more high cloud fraction. You can see that if your convective parameter, convective tuning, triggering is less, and microphysics triggering is more, then it is elongated. You see, rather overestimated means it forms more cloud ice. So definitely it impact on the more stratiform rain. You can see here more stratiform rain. So which is not again realistic. So we cannot go on that triggering. We cannot use that much triggering.
Okay. So that is it just the ice or is it like a different?
Liquid, both ice and liquid both.
Okay.
That's why these two part. One is the CA, another is the CMA. CCA, CMA.
Okay.
So now, honestly, we can say that now we are using some DNS or another project scientist is doing recalculating that coefficient once again.
Okay.
By getting the KIPEX data.
Okay.
Because we can get this information. We want this information. Only we can simulate and to get this coefficient. So that guidance will give far better. So this actually only lower limit and upper limit. We see that how it able to modulate. Previously, people not able to think that is it possible in one microphysics triggering can do the monsoon is a gigantic volume. Dynamics is very important. So how it can change if we change simple tendency equation? Yes, it can change through latent range, through dynamics modification. So therefore, we make a set of experiment with the lower limit and with higher limit, higher regimes.
Thank you, sir. One more thing, it was a very good presentation and like very good understanding. I could connect the observations to the model better. Thank you so much.
Okay, thank you very much. Thank you.
Any more questions from the? I think I have one question that how good in estimating the warm clouds, because more or less we have talked about the ice cloud fraction and the snow cloud cover during the monsoon phase system. So what about the warm clouds estimations from the CFS V2 model simulation?
Yes, CFS V2 actually mostly warm cloud, you can say.
Okay.
More warm cloud, less cold cloud.
Okay.
The control. So that was the target. That, but as per observation, you can see the observation is telling that there is a 50-50. You can see here this one is a field and hemisphere. Is a right observation. You can see there is a 50-50. So, but model is telling more warm rain, less cold rain. Okay.
But
so,
when you simulate the regional like WRF and all, then we'll get a more ice.
Different. That is different. Absolutely right.
Yes, then we'll get a more cloud, more ice, dropel, all hydrometers are very large in quantity.
Absolutely right. Because their microphysics is more, you can say, detailed.
Okay.
But WRF is more detailed microphysics, but in CFS is a very simplified microphysics. As I shown you that we have to have changed so many changes we have made it here. So
Okay.
it was very simple scheme. But
Okay.
there is a limitation. Global
Yes, of
model,
course. Global model.
global model, you cannot solve all the tendency equation. It will take huge time. So you have to manage the computation time, your solving equation, etc. So therefore you need to implement one by one and say that your lead time will not be affected, and at the same time result will be better.
Yes.
Okay. And the WRF microphysics scheme, any scheme is more complex, means more tendency equation are there.
Yes.
Yeah.
Then how we are always talking about the vertical profile of the heating, which is very much important in estimation. So whether the CFS model is accurately giving the vertical profile of heating, how good actually it is.
No, not accurately. That's why that you can get the cold bias. That's why you get the cold bias. This cold bias is due to the upper level heating is weak.
Okay.
So our target is to improve, not exactly with observation, but to improve this cold bias. And it can improve by improving this heating. Suppose this one, this Q1. So if just once you add the ice, then you see upper level heating Q1 is nearly 0.7, 0.8 degree. So this is very good.
Okay.
See, Dr. Hazra, this is Jyoti.
Okay.
See, I'm a non-expert. Can you go back to that model diagram?
For monsoon?
Yeah. This the block diagram where you had snow, ice, all that.
Okay. Okay.
No, previous one. There was one. No, you just showed, no? Just few minutes back you were showing.
Okay. This one?
Yeah.
Okay.
So let me understand what you are trying to model. So what you are saying that from the cloud ice, you are actually precipitating snow. On the way, it melts and becomes rain. Is that what you are saying?
Exactly.
So, but then how do you form snow out of ice?
No, first ice, then snow.
Yeah, so ice is there in the cloud, let's say.
Yes.
Now from there, so how do you form snow? It has to melt to form snow, right?
No, there is two ways. One is called the collection of cloud ice. You see, this is mentioned. Collection of cloud ice.
Achha, that forms the snow.
Yeah.
Okay.
So these are the sorry. Here you can see this.
Okay.
So that will form the snow. Now question is, your question is very nice question. I am really happy to see this type of question. So then this collection of cloud ice need to be reparameterized based on the type of convection.
Okay.
And then snow accretion means if cloud ice collide with cloud drops. So that is called accretion. So then also bigger. So what is the difference? Cloud ice small, then bigger is the snow, and bigger is the group L. All are ice, but as per the size, we name it. It is cloud ice, it is snow, and it is group L.
Yes. Okay. Yeah, got it. So the property will be different from because the sizes are different.
Yeah, cloud ice cannot melt. It have to make a snow. Correct. So our target is to form the snow. So we can make another hydrometer group L also. But for global model, we need less complex cloud scheme so that the because this is a globally running. So the time should be important. So we make, it's group L also club with the snow category.
Yeah. Just another related question, but nothing to do with the great science. Many a times these rains also turn back to ice because of lower temperature at ground level.
Right.
So, I don't know. That kind of thing is very common in polar regions, I think.
Yeah, but sir, I can say one thing that I think you are much better than in paleoclimate. So it's basically the stratiform rain is very to identify the stratiform rain. There means the what is called that isotope. So isotope also the delitino is also important. So that actually related to all this freezing, rhyming, condensation,
the processes can be traced.
Exactly,
Yes.
exactly.
Okay.
So if we get, that will be more real observation.
So you have to sample it there.
Yes.
It's not the okay, cloud sampling.
Yeah.
Okay.
Yeah.
Okay, thank you, Dr.
Thank you very much. Thank you, sir. Thank you very much.
Yeah. Any more questions from the audience? Okay. If not, we'll wind up the session. So I'll take the opportunity to thank Dr. Hazra for delivering the Earth Science Forum presentation on a short notice invitation and accepting in 1 second. Actually, I just asked him and he agreed. So
Thank you.
On behalf of director and all staff, students, I am extending a wholehearted thanks to Hazra sir for accepting and delivering the lecture on the Earth Science Forum. Thank you once again.
Thank you. If you have any question, you may reach me through email also. Thank you very much.
Sure. I'll communicate to the audience.
Okay. Thank you. Okay.
Thank you. Bye. Thank you, sir.
Okay. Bye.